Usually when we talk about the night sky, there's this expectation of, well, simplicity.
Simplicity.
Yeah, it's like throwing a rock into a completely calm, perfectly still pond.
Right, the ripples just spread out.
Exactly. A star shines and the light ripples out into the dark in these perfect, you know, infinite expanding spheres.
Yeah, and we've been told this story so many times that it feels intuitively right.
It really does. The circle, the sphere, I mean, it's clean. It just makes sense.
It is deeply comforting. As humans, we really like things to be smooth.
Oh, absolutely.
We like our reality to be continuous and predictable. We desperately want our classical geometry, the stuff we learned in middle school, to be mathematically clean.
And universally applicable.
Yeah.
Right. Like
Yeah.
they should work everywhere.
Exactly. But then, you start looking incredibly closely at the very fabric of how that light actually travels across the cosmos.
Okay.
You look at the math underlying the vacuum of space, and suddenly, well, that perfect sphere, it starts to look like a trick of the light, an illusion.
Wow. An illusion.
Yeah. If you scratch the surface of standard cosmology, you might find yourself looking at a landscape that is entirely geometric, rigid, highly structured, and honestly, profoundly strange.
Well, welcome to the deep dive, everyone. I'm so glad you're here with us today because we are looking at a document that, quite frankly, fundamentally challenges that smooth pond version of the universe that you and I were taught.
It really does.
We have our hands on a dense, incredibly ambitious physics paper by George James Dukas. It's titled Light Signaling Across the Universe. And it outlines something called the Transdimensional Unified Field Theory version 2.
That's a mouthful.
It is. So because we don't want to say that 50 times today, we're just going to call it TDUFT.
Which is much better. And TDUFT is this genuinely fascinating theoretical candidate.
Yeah.
To understand why it's so radical, we really have to ground ourselves in what standard physics tells us first.
Right. We need a baseline.
Standard cosmology tells a very specific, rigidly defined story about reality,
The expanding balloon stuff.
Exactly. It says light travels at an absolute constant speed, the universe is expanding like a balloon, physically stretching the space between galaxies, and crucially, light spreads out in perfect spheres governed by the mathematical constant pi.
Right.
TDUFT attempts to completely rewrite every single one of those rules.
Every single one.
All of them. It redefines cosmic light, geometry, and the very concept of entropy from the ground up.
So the mission today is to figure out what happens if all of those foundational assumptions, the expanding universe, the perfect spheres, the constant speed of light, what if they are just, I don't know, mathematical illusions?
Right.
What if they're just the 3D shadow of something vastly more complex?
It is a profound departure from general relativity and quantum field theory. Dukas's framework replaces our classical pi-based spherical universe with an 8-dimensional lattice.
An 8-dimensional lattice, okay.
Yeah, and instead of pi, this theoretical lattice is based on phi, the golden ratio.
Okay, I'm gonna stop you right there.
Yeah.
You just said we're throwing away pi.
I did. I absolutely did.
That feels entirely illegal. I mean, you can't just throw out pi.
It sounds crazy, I know.
Standard physics relies on pi for basically everything that involves curves, circles, or spheres. It's like the absolute cornerstone of how we understand the physical spread of anything in three-dimensional space.
It is.
So before we talk about dimensions and lattices, I really need you to explain how a physicist can just banish the most famous number in mathematics.
Well, to understand why Dukas banishes pi, we have to look at why standard physics uses it in the first place, right?
Okay, fair.
In standard astrophysics, when you calculate how light spreads out from a star, you use something called the isotropic inverse square law.
Isotropic meaning the same in all directions.
Exactly. You imagine a star as a perfect point, and the light is a sphere expanding outward equally in every possible direction.
A smooth pond.
The smooth pond. If you want to know how bright that light is at a certain distance, you divide the star's total luminosity by the surface area of that expanding sphere.
The surface area of a sphere is 4 pi r squared.
Exactly. So that factor of 4 pi, which is roughly 12.56637, is deeply baked into the fundamental calculation of how light moves across space.
Right, because we just assume the star is radiating equally, creating this perfect growing bubble.
Precisely. But TDUFT completely rejects that premise. It throws out 4 pi entirely.
Because it doesn't think it's a bubble.
Right, because it completely rejects spherical symmetry at the foundational level.
Right.
Instead, TDUFT argues that emission is fundamentally anisotropic.
Anisotropic, meaning it is highly directional.
Yes. It doesn't travel in a smooth, continuous bubble. It travels through a structured, rigid framework,
Yeah.
specifically an eight-dimensional lattice that features a tetrahedral emissions structure.
So, wait, I'm trying to visualize this. It's like, we've always assumed a disco ball is a perfect sphere just because when it spins, it casts light absolutely everywhere in the room.
Oh, that's a good analogy.
Right. If you stand back, the room is evenly illuminated, so you assume the source is perfectly round.
Mm-hmm.
But TDUFT is saying if you walk right up to that disco ball, you see it's actually made of flat, rigid, geometric mirrors. It's angular. It has corners. It has structure.
That is a brilliant way to conceptualize it. At a distance, the aggregate effect looks smooth, but fundamentally, at the granular level of the lattice, it is angular and geometric.
That is wild.
Right. TDUFT argues that pi is strictly a measure of circular and spherical geometry because the universe's foundational structural lattice is neither circular nor spherical.
Because it's tetrahedral and eight-dimensional.
Exactly. Because of that, pi has absolutely no physical place in the fundamental equations of light propagation. It's not just minimized, it is completely absent by construction.
Okay, my brain is already hurting a little, but I'm with you.
Yeah.
But if we aren't using pi, like if we aren't using 4 pi to represent the sphere, what number are we using to calculate how light spreads?
Do you have to have a constant to replace it?
Yeah, exactly. You can't just have a blank space in the math.
Dukas introduces a completely new geometric operator to replace 4 pi. It's called gamma phi psi, or sometimes it's referred to in the text as the geometric kappa.
Geometric kappa. Okay.
In what the paper calls the high coherence limit, which just means the localized conditions where light is behaving most stably.
Like right near a star.
Exactly, like right near a star. Under those conditions, this new geometric operator has an exact fixed numerical value of 12.57.
12.57. Hang on. Standard 4 pi is 12.566.
Mm-hmm.
Those are suspiciously close to each other.
They are incredibly close, and that numerical proximity is exactly why classical physics has been able to use 4 pi so successfully for centuries without realizing the underlying structure might be different.
Wow.
But the way TDUFT arrives at 12.57 has absolutely nothing to do with circles or spheres.
Well, break that down for me. If I'm not drawing a circle and measuring its circumference to get pi, where on earth does the number 12.57 come from?
It comes from a highly specific combination of pure dimensional geometry and something called dimensional entropy. Let's start with the geometry.
Okay, let's do it.
The TDUFT framework describes reality as a descent from 8 fundamental dimensions, what it calls D8, down to our observable lower dimensions.
Got it.
This descent happens through 6 distinct geometric steps, or cascades, of a tetrahedral structure.
A tetrahedron being like a pyramid with a triangular base, right?
Yeah.
4 faces.
Correct. Now, each one of these 6 cascades carries a topological property called an Euler D2 invariant.
Euler, as in Leonhard Euler, the famous 18th century mathematician.
The very same. Euler's formula for convex polyhedra, like our tetrahedron, is a beautiful, simple rule.
I vaguely remember that.
It's just vertices minus edges plus faces always equals 2. Let's take a cube just as an easy example.
Okay, a cube.
A cube has 8 vertices, 12 edges, and 6 faces. 8 minus 12 is -4 plus 6 equals 2.
Right.
It doesn't matter what shape you use, as long as it's a convex polyhedron, that invariant is always exactly 2.
Okay, I remember this from high school geometry. It's a universal rule for 3D shapes. But, what does it have to do with light moving across the universe?
In standard physics, nothing. But in TDUFT, this invariant of 2 encodes a fundamental dimensional field clause. It acts as the mathematical anchor for the lattice.
Okay.
So in the TDUFT model, you have 6-dimensional cascades to get light into our observable reality.
Right, and each cascade contributes this topological invariant value of 2.
Exactly. 6 cascades times an invariant of 2 equals exactly 12.
Okay, 12. Just counting the flat geometric properties of these structures as they cascade down, that's a very nice, clean integer number.
It is.
But you said the geometric operator is 12.57. We are missing 0.57. Where does the rest of the math come from?
That is where the golden ratio, phi, enters the framework.
Oh, there is.
The remaining 0.57 is a phi progression entropy operator.
It's a golden ratio. 1.618, the number we see in seashells and the spiral of galaxies in architecture.
Yes. TDUFT uses phi as the fundamental scaling mechanism of the universe. The 0.57 is a highly specific mathematical multiplier derived entirely from phi series recursion.
Meaning it builds on itself.
Exactly. It represents a precise entropy offset a structural shift that occurs as the geometry scales.
Okay, I think I see.
When you take the pure geometric baseline of 12 and add that specific phi-based entropy offset, you land at exactly 12.57.
So just so I am totally clear here, and so you listening can picture this, the number 12.57 has absolutely nothing to do with the sphere.
Nothing at all.
It is the numerical projection, or like the mathematical shadow, of an 8-dimensional tetrahedral lattice pushing light down into our 3-dimensional observable space.
That is exactly what the paper claims. When you project an 8-dimensional lattice down into a 3-dimensional observation, the expansion and contraction axes of that complex geometry balance out.
They cancel each other out.
Sort of, yeah. The tetrahedral structures, because of how they sit adjacent to one another, distribute the light emission evenly. The end result is a shape that mimics a perfect sphere almost flawlessly.
But underneath it is fundamentally built from flat, angular, phi-based geometry.
This is genuinely blowing my mind a little bit. We've been using pi this whole time because a sphere was just a good enough approximation for the 3D shadow of an 8D structure.
Yes.
We've been mistaking the shadow for the object.
It's a paradigm-shifting way to view reality, but it also introduces massive logical cascade effects.
I can imagine.
If you fundamentally change the geometry of how light spreads,
Yeah.
if you throw out the sphere and bring in the lattice, you don't just change the shape of the universe.
What else changes?
You have to change the rules for the speed of light itself.
Okay, right. Because if the track that the light is running on changes from a smooth, continuous surface to a rigid, jagged dimensional lattice, the speed limit has to work differently.
Exactly.
Let's dig into that, because in standard physics, c, the speed of light in a vacuum, is the ultimate, untouchable, fundamental constant.
It is the bedrock of Einstein's general relativity. Exactly. 299,792,458 meters per second. Right. It's the universe's absolute speed limit. Nothing can go faster. It's a raw, given fact of nature. But you're telling me TDUFT says that's also an illusion.
In classical physics, c is just a raw number you plug into equations. But in TDUFT, the speed of light is not just an arbitrary, fundamental constant.
What is it then?
It is modeled as a coherence-dependent projection that is governed by something called a Ramanujan-Dukas attenuation kernel.
Okay, I have to stop you. Ramanujan-Dukas attenuation kernel.
I know it's a lot.
I know Ramanujan was a brilliant mathematician, but that phrase sounds like a piece of equipment that powers a sci-fi spaceship. What is an attenuation kernel actually doing to the light mechanically?
It sounds intimidating, but the concept is actually quite elegant. Think of a kernel in mathematics as a core engine or a filter that transforms one thing into another.
Okay, a filter.
An attenuation kernel is a mathematical engine that dictates how a signal weakens, how it attenuates as it moves through a medium. In TDUFT, the formula for the speed of light starts with a pure base scale of exactly 10 to the power of 8 meters per second.
Wait, so just a flat 10 to the 8?
Well, 3 times 10 to the 8 to be exact. The math modifying that base scale is a complex series built entirely on phi. Under maximum coherence, meaning the absolute most pristine condition the lattice can be in, this phi-structured engine perfectly mimics the classical speed of light.
So it arrives at the exact same speed, but the reason it travels at that speed is completely different.
Exactly. And this is where the paper fundamentally redefines the concept of entropy. We are so used to thinking of entropy as statistical disorder.
Right, the classic examples like a glass shattering, an ice cube melting in a warm room, heat dissipating, the universe constantly moving toward chaos.
Yes, thermodynamic entropy. But TDUFT defines entropy as dimensional resistance.
Dimensional resistance.
Yeah.
Meaning, but it's a physical toll.
Friction.
It is a literal cost paid when perfect high-dimensional geometry descends into lower-dimensional physical reality.
Let me make sure I follow. Let's trace a photon in this theory. The photon originates in an 8-dimensional space, D8. But to propagate, to actually move and be observed in our lower dimensional space, D2, it has to descend through a dimensional ladder.
Right, the cascades we talked about.
Yes. That dimensional descent isn't free. It costs energy. It costs what the paper calls coherence.
Okay, I want to see if I can translate this. Let's imagine this like currency exchange.
Okay, let's hear it.
Let's say I have exactly $300. That is the pure, mathematically perfect geometric ideal represented in this theory by the number 3, scaling up to 3 times 10 to the 8th meters per second.
A very strong starting point.
That's my perfect $300 in the 8-dimensional economy. But I want to spend that money in the real-world physical economy of our lower dimension.
Right.
I can't just walk across the border for free. To bring that money into our dimension, I have to walk through a dimensional customs booth. And the customs agent, the dimensional resistance, takes a tiny, incredibly exact cut. Am I understanding that right?
You are. You are spot on. In the source material, this customs agent's cut is called the emergence constant, or epsilon.
And what is the exact cut? Because if I have 300 pure geometric dollars, but the physical speed of light is 299,792,458 meters per second.
Epsilon is precisely the mathematical difference between the pure geometric number 3 and the observed physical speed of light, which is 2.99792,458.
So the toll paid at the dimensional border is exactly 0.000007542.
Exactly. You step out of the booth, the agent takes their 0.0007542 cents, and you are left with exactly $299.79, the physical speed of light.
That is wild. So the speed of light is literally just the speed of perfect geometry paying its taxes to exist in reality.
What is truly fascinating here is how literal that calculation is in the text. TDUFT asserts that the speed of light isn't just some random limit that happened to settle at 299 million meters per second through happenstance.
Right.
It is the pure geometric maximum, the number 3, minus the exact dimensional toll of emergence.
That is a wild way to look at physics.
It reframes everything. And there are actually 3 of these entropy operators in the framework, each exacting a specific toll on the system.
There were more taxes.
Yes. There is the emergence constant you just mentioned, epsilon. Then there is the phi progression entropy, epsilon phi, which we talked about earlier when we were adding that 0.57 to our baseline geometry of 12.
Right, the 12.57 thing.
Exactly. And finally, there is the time lattice entropy, epsilon prime, which represents the specific cost of temporal contraction. Together, these 3 operators represent total dimensional resistance.
So entropy isn't just random disorder or things breaking down. It's the systemic friction of squeezing 8-dimensional math into a 3-dimensional observable universe.
Yes. And that redefinition has massive universe-breaking implications.
How so?
Because if light is constantly paying this toll, if it is constantly experiencing dimensional resistance and losing coherence as it travels from node to node through the lattice, it means the signal gets weaker over distance in a way classical physics just doesn't account for. In the framework, this ongoing attenuation is governed by a kernel called E of R.
E of R, okay.
As the distance r reaches infinity, the coherence of the light, E of R, drops aggressively towards 0.
Which brings up a really terrifying, exciting question. If the light from a star is constantly paying this toll, constantly losing its coherence the further it travels across the lattice,
Yes.
what happens when it completely runs out of currency? What happens when we try to look into deep, deep space way beyond our local galaxy?
This is where TDUFT aggressively diverges from standard astrophysics. To understand the contrast, we need to talk about standard cosmology's FLRW metric.
FLRW, that stands for Friedman, Lemaitre, Robertson, Walker, right?
Yeah.
The scientists who developed the model.
Correct. The FLRW metric is the foundational mathematical model of our current cosmological understanding. It explicitly assumes that the universe is physically expanding. It uses something called metric expansion of space. Think of the universe like a loaf of raisin bread baking in an oven. The raisins are galaxies.
I've heard this one.
As the dough expands, the raisins move away from each other. The raisins aren't swimming through the dough itself is stretching.
Right, space itself is getting bigger. The galaxies aren't flying away. The space between them is growing.
Because of that metric expansion, classical physics dictates that there is a cosmological horizon. This is a physical, hard limit to how far we can possibly see in the universe.
Because the space beyond that horizon is receding away from us faster than the speed of light.
Exactly. Light from beyond that, no raisin bread. There is absolutely no metric expansion in this framework. Space is not stretching. Instead of a cosmological horizon caused by expanding space, TDUFT introduces a concept called a detectability radius, or a blackout radius.
The blackout radius,
Right.
because the light isn't trying to outrun expanding space, it's just getting tired.
Essentially, yes. Because the light constantly loses coherence due to that dimensional entropy, that tax we talked about, the E of R value drops the further it goes.
Okay.
Eventually, there is a hard physical limit where the signal's intensity falls below the absolute minimum detectable threshold of the universe.
There's a minimum threshold.
Yes. The source material mathematically defines this minimum intensity, I sub min, as 10 to the negative 20 watts per square meter. Beyond a certain distance, the light just loses all its coherence and fades into the background lattice.
It's not that the universe ends there or that space is rushing away from us like a tidal wave. It's just that the light signal drops below the absolute minimum threshold of physical reality.
Correct.
It hits the blackout radius and ceases to be observable. Does the paper give examples of how far that actually is?
It does, and it starts with a benchmark we understand very well: our own sun.
Okay, let's hear it.
Using the TDUFT directional intensity law, Dukas calculates the maximum possible distance you could theoretically detect a star with the exact luminosity of our sun. That solar blackout radius is calculated to be roughly 5.83 million light-years.
Wait, 5.83 million?
Yes.
So if you were standing 6 million light-years away, looking directly at our sun with a theoretically perfect telescope, you would see absolutely nothing.
Nothing at all.
The sun's light has paid too many dimensional tolls, lost its coherence, and vanished from the lattice entirely.
Yes, even under the maximum theoretical coherence assumptions, it simply fades out. But where this gets truly mind-bending is when the paper applies the same framework to a much more extreme cosmological example:
Ooh, what is it?
a galaxy known as MOM Z14.
Okay, let's talk about MOM Z14. For you listening, this is a real, immensely massive, extremely high redshift galaxy that was recently discovered by the James Webb Space Telescope.
It's a fascinating object.
It is currently one of the most distant, oldest things humanity has ever seen. What does TDUFT say about this ancient galaxy?
Let's look at the standard NASA and JWST cosmology first. Based on its redshift, standard physics calculates the luminosity distance of MOM Z14 at about 13.5 billion light-years away.
Right, it's sitting right near the edge of what we consider the dawn of the universe.
But when Dukas takes the exact same UV magnitude data of MOM Z14 and plugs it into the TDUFT phi-psi inverse square model, using the blackout radius formula,
Yeah,
the result is staggering.
I'm bracing myself.
The calculated blackout radius for MOM Z14 in this framework is approximately 8.47 times 10 to the 11th light-years. That is 847 billion light-years.
I need to make sure I'm hearing that correctly. 837 billion light-years.
Right.
That is vastly, massively larger than the standard edge of the observable universe.
Yeah.
We just said the classical particle horizon is 46 billion light-years.
Yes, it is.
TDUFT is saying this galaxy's light could theoretically travel 847 billion light-years through a static lattice before blacking out. That makes the universe functionally ancient or infinitely large compared to standard models.
It completely reshapes the scale of reality. And the text strongly emphasizes that this distance is a pure detectability threshold based entirely on the physics of the light itself.
So it's not a causal limit.
No, it is not a causal horizon created by the Big Bang or a suddenly expanding universe. It's just the raw physical distance the signal can push through the 8-dimensional lattice before dropping below that 10 to the negative 20 watts per square meter intensity threshold.
Okay, I have a massive problem with this, or at least a major question.
Sure.
If TDUFT radically changes the distances of these objects, or at least the mechanism of how we measure their light over vast distances, does it change the physical size of the galaxy itself?
What do you mean?
Like when we look at MOM Z14 through JWST, we see it takes up a certain amount of visual space on the sensor. If the geometry of how light reaches us is totally different, is the galaxy physically bigger or smaller than NASA thinks it is?
It is a vital, critical question to ask of any new cosmological model,
Yeah.
and the source material actually devotes a specific section to geometric size.
Oh, good. What does it say?
The paper is incredibly intellectually honest here. Dukas explicitly states that you actually cannot calculate an independent geometric size for MOM Z14 using the TDUFT framework yet.
Wait, really? Why not? If we have a new set of rulers, why can't we just measure the galaxy?
Because of the limitations of our current observational data, JWST only provides an angular size.
Angular size.
Think of angular size as how big something appears from your specific vantage point, like holding your thumb up to block out the moon.
Right.
Classical physics takes that angular size and converts it to a physical size of roughly 251 light-years across, based entirely on standard expanding universe distances. But to calculate a purely TDUFT consistent physical radius, you can't just use the luminosity and the angular size. You need an independent variable.
What's the missing variable?
A specific effective temperature or surface brightness temperature for the galaxy as a whole.
We don't have that data.
No, that specific baseline hasn't been established with sufficient precision in the JWST data for this object. Without an independent effective temperature, the TDUFT luminosity equation cannot be mathematically inverted to yield a definitive geometric size.
So the paper is effectively saying, we have a fundamentally better ruler, but astronomy hasn't provided all the raw data points we need to use it on this specific hyperdistant galaxy yet.
Exactly.
That's fair. I appreciate a theory that knows its own current limitations based on observational data. But wait, this brings up a massive, glaring, unignorable issue.
I suspect I know what you're going to ask.
If TDUFT says the universe isn't expanding in the classical FLRW sense, no stretching space, no raisin bread, just static dimensional resistance on a rigid lattice, how on earth does Dukas explain redshift?
The redshift illusion.
Yes, because for those of you who might be rusty on astrophysics, redshift is the absolute smoking gun of modern cosmology.
It is.
It is the very phenomenon Edwin Hubble used to prove the universe is expanding. You can't just say space isn't expanding without explaining away a century of redshift data.
Let's lay out the standard physics explanation of redshift first, just to be incredibly clear about what TDUFT is up against.
Please do.
When we look at distant galaxies, the light coming from them is shifted toward the red end of the electromagnetic spectrum, meaning the wavelength of the light is longer than it was when it was emitted by the star.
Right. Blue light is compressed, high frequency. Red light is stretched out, lower frequency.
The standard classical explanation for this is cosmological redshift. Going back to our raisin bread analogy, because the literal fabric of space is stretching as the universe expands, it physically stretches the wavelength of the light traveling through it.
The analogy I always use is drawing a squiggly wave on a rubber band with a Sharpie.
I like that one.
If you hold the ends of the rubber band and pull them apart, the physical wave you drew literally gets longer and wider. The wavelength stretches. The light becomes redder. That is standard cosmology.
Exactly. But TDUFT completely and entirely rejects metric expansion. The rubber band isn't stretching. Space isn't moving.
Okay, so what is happening?
So the theory has to explain redshift via an entirely different mechanism. In TDUFT, redshift is not caused by moving space. It is described as a lattice wave relational change. It is a path-integrated attenuation.
I need to stop you there. We are back in the heavy jargon, lattice wave relational change.
I know, it's dead.
What is actually physically happening to the photon as it moves across the universe if the space around it isn't stretching?
In the eight-dimensional phi lattice, a photon isn't just a free-floating wave stretching out in empty space. It is a stabilized local frequency residing at a specific node on the lattice.
A node.
Think of the lattice as an incredibly dense grid of intersecting points. As the light signal propagates from emission at the star to detection at our telescope, it travels by interacting with intervening lattice nodes.
Okay.
The framework states that redshift is actually a change in the stabilized alignment state of the photon node due to cumulative rebalancing and attenuation along that specific path.
Okay, I think I have a way to conceptualize this. Let me try to translate this for you listening. Standard physics is the rubber band. The literal ground you were standing on is stretching beneath your feet, which stretches the wave.
Right.
TDUFT, however, is more like a message being passed down a massive line of people, like a cosmic bucket brigade.
Go on.
The people in the line are the lattice nodes. They are standing perfectly still. The ground they are standing on isn't moving or stretching at all.
Correct.
But as the message gets passed from person to person, billions and billions of times over billions of light years, the message gets slightly garbled, or the tone of the message shifts slightly due to the sheer friction and effort of passing it along.
Yeah.
The energy required to hand off the signal changes the frequency of the signal. That garbling, that shift in tone, is what we see as redshift.
That is a highly effective, deeply accurate analogy. The physical ground hasn't moved an inch, but the signal has degraded through interaction. The text calls this a global attenuation functional.
Wow.
The longer the path, the more people in your bucket brigade, the more cumulative lattice attenuation occurs.
So Hubble saw that things further away were redder,
Yeah.
and he assumed they were moving away faster.
Yeah.
But TDUFT says they are redder just because the light had to go through more lattice nodes to get here.
Exactly. For relatively short distances, this attenuation effect looks perfectly linear, which mathematically mimics standard Hubble expansion almost exactly.
For long distances.
For massive cosmological distances, the attenuation becomes nonlinear. And crucially, this means that in TDUFT, distance calculations and redshift calculations are completely independent mechanics.
Wait, independent. But in standard physics, redshift literally is distance. Higher redshift equals further away, because the further away it is, the faster space is stretching it. They are inextricably linked.
Not in TDUFT. In this framework, distance is purely geometric and luminosity-based.
Based on the inverse square law.
Right, it's determined by the inverse square law, the 12.57 geometric operator, and the entropy drop we discussed earlier. Redshift, on the other hand, is alignment-based and attenuation-based.
That's a huge difference.
The text explicitly states that redshift does not automatically modify the TD-UFT luminosity distance unless you intentionally manually insert an attenuation factor into the calculation.
That is a massive conceptual leap.
They are compatible within the theory, but structurally separate phenomena. Redshift is just the wear and tear of travel, the friction of the lattice. It is not a measure of stretching space.
This is a monumental shift in perspective. You are basically saying that for the last 100 years, we've completely misread the speedometer of the universe.
It's a bold claim, yes.
But this leaves us with an elephant in the room, a massive, glaring question that I'm sure anyone listening who knows astronomy is screaming right now.
Let's hear it.
If this TD-UFT model is so radically different, if it throws away pi, throws away the expanding metric, changes the entire nature of light speed, and redefines redshift entirely,
Yeah.
how is it not instantly definitively disproven by our everyday astronomical observations? We launch telescopes into space every single day. We measure stars constantly.
Very true.
If pi was wrong, wouldn't we notice?
Mm.
If 4 pi is completely inaccurate, shouldn't every local satellite measurement we take be breaking down?
That is the exact critical question that Appendix J of the source material addresses. And honestly, it is arguably the most brilliant or perhaps audacious part of the entire paper. It's the Gaia benchmark test.
Let's talk about Gaia, because for you listening, Gaia is an incredible European Space Agency observatory.
It really is an engineering marvel.
It's a space telescope whose whole job is astrometry, precisely measuring the positions, distances, and motions of over 1 billion stars in our local Milky Way galaxy. It is widely considered the absolute gold standard for local astronomical distances.
Yes, the data is impeccable.
If your new radical physics theory cannot flawlessly match Gaia's data, your theory is dead on arrival.
Exactly. Dukas knows this. TD-UFT must be able to reproduce classical stellar luminosities and geometric distances for nearby stars, specifically main sequence stars whose distances are independently physically verified by Gaia's parallax measurements.
Real quick, parallax is just geometry, Rex. It's
Yeah.
holding your thumb up, closing one eye then the other, and seeing how your thumb moves against the background.
That's exactly it.
Gaia does that as the Earth moves around the sun to measure distance without needing redshift or luminosity. It's pure triangulation.
Precisely. It is hard geometric fact. And according to the source material's rigorous calculations in Appendix J, TD-UFT perfectly matches classical physics in this regime. It recovers the exact same distances and luminosities that Gaia observes.
How is that mathematically possible? You just spent 40 minutes telling me TD-UFT uses a completely different underlying geometry.
It comes back to what the paper calls the high coherence regime.
Right, you mentioned that earlier.
For nearby stars in our local neighborhood, we are looking at relatively stable atmospheres, low structural anisotropy, and crucially, very short distances where the coherence loss, that E of R dimensional entropy toll, is effectively negligible.
Because it hasn't traveled far enough to pay a lot of tolls.
Exactly. For local measurements, E of R practically equals 1. In this localized best-case regime, the mathematical framework of the 8D lattice collapses into an operational form that mimics classical 3D physics flawlessly.
But the hard numbers. We established at the very beginning that classical physics uses 4 pi, which is 12.56637.
Right.
TD-UFT uses the geometric operator gamma phi psi, which is 12.57. There are different numbers. If you plug different numbers into the telescope's computer, you should get different results.
And that is the crux of the entire argument. The absolute mathematical difference between those two numbers, what the paper calls the projection residual, is roughly 0.00363.
A tiny fraction of a percent.
Yes, and that specific variance is well below the detection threshold of our current most advanced Gaia measurements.
Wait, really?
The error bars, the inherent margin of error on Gaia's measurements for effective temperature, stellar radius, and bolometric flux, are mathematically larger than that 0.00363 difference.
I am stunned. You're telling me it's hiding. The 8-dimensional universe is literally hiding in the margin of error of our best 3D measurements.
If we look at the historical context, TD-UFT is arguing that 4 pi was always just a local approximation.
Wow.
Humanity used pi because spherical symmetry seemed correct when we look at local stars, and our instruments simply weren't precise enough to see the jagged 8-dimensional edges of the underlying geometry.
The mirrors on the disco ball.
Yes. The deeper reality is an 8-dimensional lattice. But when it projects down to our 3D observations, the expansion and contraction pairs of the geometry balance out perfectly.
Okay.
The tetrahedral adjacency distributes the emission evenly, and it just happens to look almost exactly like a sphere to our local telescopes.
It's a mathematical mask.
Yeah.
You listening to really think about what this implies for a second. Every single time you look up at a star in the night sky, you inherently assume its light is radiating towards you in a perfect, smooth sphere.
Hmm.
Dukas is arguing that you're actually looking at the three-dimensional shadow of an eight-dimensional geometric lattice.
Uh-huh.
And it just perfectly mimics a sphere because the mathematical discrepancy is a fraction of a percent. The universe is playing a profound geometric trick on our eyes and our instruments.
The paper acknowledges this directly and boldly. It states that the Gaia test effectively converts an internal consistency argument into external validation.
Because it doesn't break local physics.
Right. By successfully recovering the Earth-Sun distance and perfectly matching Gaia parallaxes for main sequence stars within the established measurement error, the theory mathematically proves it is observationally indistinguishable from standard physics in our local neighborhood.
Okay, but this creates a massive philosophical and scientific paradox. If a new theory is utterly indistinguishable from the old theory locally, how do we ever prove the new theory is actually real?
That's the challenge.
How do you test a radical theory that perfectly mimics the old rules?
You have to push it to the absolute extremes. The framework can absolutely be falsified or verified, but you cannot do it by looking at our local stars.
Where do we look?
You have to look far outside the high coherence regime. You have to look at extreme cosmological distances where that E of R coherence drops significantly enough to be measured.
Like MOMZ 14.
Exactly, or you have to look at cosmic sources with extreme structural anisotropies, things like quasar jets or ultra-rapid rotators.
Chaotic environments.
In those extreme chaotic environments, the TDUFT 12.57 geometry will theoretically begin to violently and measurably diverge from the classical 4-pi geometry. The paper actually lays out a priority list for external validation, suggesting we need to apply this model to high redshift luminosity measurements from James Webb to hunt for those exact measurable deviations.
So to prove the lattice exists, we have to look at the very edges of reality, to the most distant, ancient light we can find, to see the lattice finally peeking through the illusion. That is incredible.
It is a meticulously constructed theoretical candidate. It doesn't just throw out ideas. It offers a unified field equation, a shell-indexed master equation, that attempts to tie all of these radical concepts together.
The altered speed of light, the dimensional entropy, the attenuation of redshift, the geometric structure.
It is mathematically dense, it is entirely dimensionless, it is completely pi-free, and it aggressively challenges us to reconsider the foundational shape of space.
It has been a wild ride. We've explored a completely alternative framework for reality today. One that asks us to trade the familiar comfort of pi for the recursive complexity of the golden ratio.
Indeed.
To trade smooth, perfect spheres for rigid, eight-dimensional tetrahedral lattices. To trade a violently expanding, stretching universe for a static, dimensionally resistant continuum where light doesn't stretch at all. It just slowly, inexorably pays a dimensional toll until it fades to black in the cosmic dark.
It serves as a vital reminder that our scientific models are precisely that. They are just models.
Right.
They are maps of reality, not the territory itself. When a new map proposes that the very geometry of the paper it's drawn on is fundamentally different, it forces the scientific community to reevaluate every single measurement we've ever taken. It demands rigor.
And it leaves me with a final thought, something for you to ponder the next time you step outside. Look up at the night sky and see that starlight hitting your eyes. We have built our entire understanding of the cosmos on the assumption that the local rules we observe right here, like spherical geometry and the mathematical perfection of pi, scale infinitely and perfectly across the entire universe.
It's a huge assumption.
We assume the pond ripples forever in the exact same way. But if a completely different eight-dimensional lattice can wear a mask that perfectly mimics a 3D sphere to our most advanced billion-dollar telescopes, how do we ever truly know the underlying shape of reality? Are we actually seeing the universe exactly as it is, or are we just seeing the absolute hard limits of our own dimensional perspective?
A vital, profound question for the future of astrophysics.
Thank you for joining us on this deep dive. Keep questioning the world around you, keep looking closely at the shapes and the math you take for granted, and we will see you next time.